Somewhere above you tonight, an entire star could be exploding, and you would never hear a single sound of it. Hello, and welcome to Somniora Mind. I'm glad you're here. Tonight, we're settling into a strange kind of comfort. The universe, for all its violence, is one of the quietest places that could possibly exist. Stars collapse, galaxies collide, black holes swallow entire suns whole. And yet, across nearly all of it, there is no sound at all. Not a hum, not a roar, not even a whisper. Just a vast, patient stillness, stretching in every direction, further than any voice could ever carry. Before we drift into why that is, 3 quiet questions to hold loosely tonight, like something you're turning over slowly rather than trying to solve. First, if the loudest event imaginable happened right next to you in space, would you hear anything at all? Second, is silence really the same thing as emptiness? Or is it doing something quietly, all on its own? Third, if the universe is growing quieter with every passing year, what does that mean for a night like this one, right now, while it's still this alive? We'll return to each of these before the night is through. For now, just let them settle, unhurried, somewhere in the back of your mind. A gentle note before we begin. Some of what we'll cover tonight is settled, well-tested physics, the kind confirmed by generations of careful measurement. Other parts sit further out, at the edge of what's currently understood, held a little more loosely even by the people who study it for a living. I'll try to keep that distinction clear as we go, because I think the honesty of it is part of what makes this particular quiet so calming rather than unsettling. If these slow hours have ever helped ease you into sleep, the kindest thing you could do is pass this along to someone else who might need a quiet night too. It costs nothing, and it helps this reach the next tired mind out there. One quiet mind at a time. For now, there's nothing left to do but let go. Let your breathing slow on its own. Let the weight of the day drain out through your shoulders, through your hands, through the backs of your knees. You don't need to hold on to anything I say. Just let the words drift past, soft and half-heard, the way distant thunder sounds when you're already halfway into a dream. Let's begin in the quietest place there is. Sound, as strange as it might feel to say out loud, cannot actually exist in most of the universe, not because it's too quiet out there, but because sound needs something that space almost entirely lacks. To understand why, it helps to remember what sound actually is. A sound isn't a thing that travels through nothing. It's a disturbance, a wave of pressure passed from one particle to the next, the way a nudge might pass down a long line of people standing shoulder to shoulder, each one bumping gently into the next. When you speak, your vocal cords push against nearby air molecules, which push against their neighbors, which push against theirs, and so on, in a chain reaction moving outward until it eventually reaches someone's eardrum and gets translated back into something the brain recognizes as a voice. Take away the air, take away the medium doing all that bumping and pushing, and there's nothing left to carry the disturbance forward at all. This is exactly the trouble with space. On Earth, even the thinnest, cleanest air still contains an almost uncountable number of molecules crammed into every small pocket of volume, more than enough to carry sound easily across a room, a field, or a valley. The space between stars, by contrast, is close to a true vacuum, often holding no more than a handful of atoms in an entire cubic centimeter, sometimes far fewer than that. There simply aren't enough particles out there, spaced closely enough together, to pass a pressure wave from one to the next in any meaningful way. A shout released into open space wouldn't echo, fade, or drift away slowly. It would simply have nothing to travel through in the first place, no medium available to carry it anywhere at all. This is part of why an event as unimaginably violent as a star's collapse or two black holes colliding produces no sound whatsoever, no matter how close you might imagine standing to it. It isn't that the sound is too faint to hear. It's that sound, in the ordinary sense, cannot exist there to begin with. Light can cross that same empty gap effortlessly, since light doesn't need a medium to travel through at all. But sound, dependent entirely on matter bumping into more matter, simply runs out of anything to push against the moment it leaves behind an atmosphere thick enough to carry it. Our own sun, standing quietly in the sky each day, is in reality one of the loudest objects in the entire solar system, and not one particle of that sound will ever reach your ears. Deep within the sun, enormous convective currents churn constantly, vast columns of plasma rising, cooling, and sinking again in a restless, endless cycle. These churning currents generate powerful acoustic waves, genuine sound, rumbling and echoing through the sun's interior in patterns astronomers have actually learned to study in detail through a field called helioseismology. By carefully measuring how the sun's surface ripples and shifts in response to these internal sound waves, scientists have mapped out layers of the sun's interior that could never be directly seen, in much the same way doctors use ultrasound to examine structures hidden beneath the skin. If you could somehow stand close enough to the sun and still survive, and if the space around it were somehow filled with enough matter to carry sound, the noise would likely be overwhelming, deep and continuous, more powerful than anything produced on Earth. But none of that sound ever reaches us, or reaches anything else beyond the sun's own churning surface. The instant those acoustic waves try to escape into the vacuum of space separating the sun from Earth, they run out of anything to travel through, and simply stop, the same way a shout stops the moment it runs out of air to carry it. So the quiet, steady presence overhead each day, the one that warms your skin and lights the whole sky, is secretly one of the noisiest things nearby, its true voice sealed permanently inside its own churning interior, never once escaping into the silence surrounding it. Two black holes can collide with more raw energy than every star in the observable universe combined releases in an entire second, and the event would still, in the ordinary sense, be completely silent. Black hole mergers rank among the most violent events physics has ever confirmed, releasing a staggering, almost unthinkable amount of energy in the instant two of these collapsed objects spiral into one another and merge. And yet, exactly as we've discussed, that event produces no sound at all, in the traditional meaning of the word, since there's no matter nearby dense enough to carry a pressure wave outward from the collision. There is, however, something else these mergers produce, something scientists have gotten into the habit of describing with sound-related language, even though it isn't sound in the technical sense at all. As we discussed on a previous night together, colliding black holes send ripples directly through the fabric of space-time itself, called gravitational waves, and these ripples oscillate at frequencies that happen to fall, once detected and carefully adjusted, within a range remarkably close to what the human ear can perceive. When scientists first confirmed a black hole merger through the detectors built to catch these ripples, they took the raw data and converted its oscillations directly into an audio file, a process called sonification, and the result was an eerie, unmistakable little chirp, rising quickly in pitch before fading into stillness, close enough to audible sound that anyone listening could recognize it immediately as something. It's important to be honest about what that chirp actually is. It isn't literally a sound that traveled across space the way a voice or a bell does. It's a translation, a scientific choice to represent an invisible ripple in space-time using the one sense best equipped to notice a rapid rise and fall in frequency. But it captures something true and rather moving about tonight's subject. Even the most violent, energetic events the universe can produce arrive to us not as noise, but as data, patiently converted, patiently translated, until something silent becomes, just briefly, something we're able to hear. There is one true exception to tonight's whole story, one place where astronomers have detected something closer to genuine sound, drifting through actual gas, at a note lower than anything the human ear could ever register. At the center of the Perseus galaxy cluster, an enormous, distant collection of galaxies bound together by gravity, sits a supermassive black hole that has been quietly, continuously disturbing the hot gas surrounding it for a very long time. Unlike the near-perfect vacuum of ordinary interstellar space, the gas filling a galaxy cluster is considerably denser, thin by everyday standards, but still substantial enough, across such an enormous scale, to actually carry sound waves, real pressure waves, rippling outward from the black hole's activity. Astronomers studying the Perseus cluster identified ripples in that surrounding gas consistent with sound waves, and when they calculated the pitch of that sound, they found something almost impossible to picture. The note was a B flat, but pitched roughly 57 octaves below middle C, a frequency so deep, so impossibly low, that it would take about 10 million years just to complete a single wave cycle. For comparison, the lowest note audible to human hearing completes many full cycles in a single second. This cosmic note is so far below anything a human ear, or any ear, could ever perceive that scientists needed to raise its pitch by many trillions of times just to make an audible version anyone could listen to. It remains, as far as anyone currently knows, one of the only confirmed instances of an actual sound wave detected traveling through the wider universe, beyond the protective, sound-carrying atmosphere of a single planet. A black hole, patiently, continuously, humming a note lower than anything imaginable, into gas so thin it would count as an excellent vacuum almost anywhere on Earth, playing on, unheard, for longer than most stars have existed. For nearly all of human history, the quiet, unchanging appearance of the night sky wasn't seen as emptiness at all. It was interpreted instead as proof that the heavens were an intricate, carefully arranged machine. The philosopher Aristotle proposed one of the most influential versions of this idea, describing the sky as a series of perfect, nested spheres, each one carrying the sun, the moon, or a particular set of stars in smooth, unbroken circular paths around the Earth. In this picture, the stillness of the night sky wasn't a sign of vast, empty distances. It was a sign of order, of a cosmos built with careful, deliberate precision, humming along quietly and perfectly, the way a well-made clock ticks along without a wasted motion. Medieval scholars inherited and expanded on these ideas, describing the heavens as filled with a mysterious, perfect substance sometimes called quintessence, distinct from the ordinary earthly elements of fire, water, air, and stone. Under this framework, the moon moved within its own sphere, the sun within another, and the most distant stars were fixed to a single outer shell that turned slowly, majestically, around everything else. It was, by design, a relatively small, complete, orderly universe, one where quietness meant fullness, structure, and purpose, rather than vast, echoing empty space. It wasn't until centuries later, through the work of astronomers like Copernicus, Galileo, and Kepler, that this tidy, nested picture began to give way to something far larger, far stranger, and considerably emptier than anyone had previously imagined. The quiet stillness overhead never actually changed. What changed, slowly, patiently, over centuries of careful observation, was what people understood that stillness to actually mean. Our entire galaxy is spinning, carrying its 100 billion or so stars in a slow, graceful rotation, and yet from where you're lying right now, none of that motion produces the faintest hint of sound or sensation at all. The Milky Way, like most large galaxies, takes the shape of a wide, flattened disk threaded through with long, curving spiral arms. For a long time, astronomers assumed these arms were simply fixed structures, rotating rigidly along with the rest of the galaxy, like the blades of a spinning fan. The real picture turned out to be considerably more elegant. The spiral arms aren't rigid at all. They're what astronomers call density waves, regions where gas and stars become temporarily more crowded together as they orbit the galactic center. Similar to the way traffic can bunch up temporarily on a highway, forming a visible cluster of cars that persists as a pattern even though the individual cars themselves are constantly entering and leaving that crowded stretch. As stars and clouds of gas pass through one of these denser regions, the increased crowding compresses the gas, and that gentle compression can trigger new star formation, filling each spiral arm with a steady trickle of bright, young stars that make the arms so visible and striking in photographs of other galaxies. Our own solar system happens to sit near the edge of one of these spiral features, orbiting the galactic center once every roughly 220 million years, an orbit so vast and so slow that the dinosaurs, all of them, lived and vanished before our solar system completed a single full lap. And through all of that motion, the spinning disk, the drifting spiral arms, the slow trillion-mile journey around the galactic center, everything remains, from where you're resting tonight, completely silent and completely undetectable without instruments built specifically to measure it. The galaxy turns, the stars drift, and none of it makes a single sound. Between the great gathering places of galaxies lie regions so profoundly empty that some astronomers describe them as the closest thing the universe has to true, absolute silence. These are called cosmic voids, enormous stretches of space containing dramatically fewer galaxies than the crowded filaments and clusters surrounding them. Some of these voids stretch across hundreds of millions of light years, vast pockets where only a scattered handful of galaxies drift, separated from one another by distances so large that light itself can take tens of millions of years just to cross the gap between neighbors. Within a void like this, an observer would find themselves cut off, in a very real sense, from most of the universe's activity, surrounded by darkness interrupted only occasionally by the faint, distant glow of structures far beyond the void's own boundaries. It's tempting to think of these voids as simply empty leftover space, gaps between the parts of the universe that matter. But cosmologists see them as something more meaningful than that, genuine, essential features of the universe's overall structure, shaped by the same subtle patterns of early density that built the great filaments and clusters in the first place, where matter gathered slightly more densely in the universe's infancy. Gravity slowly pulled even more matter inward over billions of years, forming the crowded, glittering web of galaxies we've discussed on previous nights. Where matter started out slightly sparser, that sparseness only deepened over time, as what little matter existed drifted outward, pulled instead toward the denser regions nearby, leaving these voids increasingly empty, increasingly still. In their own quiet way, these voids capture something essential about tonight's whole subject. The universe isn't quiet by accident or despite itself. In certain regions, entire volumes larger than anything a human mind can comfortably picture, quietness is simply the natural, settled state of things, undisturbed by the crowded busyness playing out in the filaments and clusters nearby. For most of the 20th century, physicists expected the universe's expansion to be gradually, quietly slowing down, pulled back by the combined gravity of everything within it. Then, in the late 1990s, two separate teams of astronomers discovered the exact opposite was happening. The evidence came from a very particular, very reliable kind of stellar explosion called a Type I supernova, produced when a certain kind of collapsed star, called a white dwarf, gradually pulls in more mass than it can structurally support and detonates with a brightness so consistent and well understood that astronomers can use it almost like a cosmic candle of known wattage, calculating precise distances based on how bright or faint that familiar explosion appears from Earth. Using these reliable stellar candles, both research teams set out to measure how the universe's expansion had changed over billions of years of cosmic history, fully expecting to find gravity gradually applying the brakes, slowing the expansion down bit by bit, the way a ball thrown upward slows as gravity pulls it back toward the ground. Instead, the data showed something nobody had predicted. Distant supernovae appeared fainter and therefore farther away than they should have been if the expansion were simply coasting along or gradually slowing down. The only explanation that fit the data was that the expansion itself was accelerating, speeding up over time rather than gently winding down. This discovery, which earned its researchers a Nobel Prize in 2011, pointed toward the existence of dark energy, the same mysterious force discussed briefly on a previous night together, now understood to be actively pushing the universe apart at an increasing rate, rather than simply allowing it to coast along on its own early momentum. It remains one of the more startling reversals in the entire history of astronomy, a moment when careful, patient measurement quietly overturned decades of confident, reasonable-sounding assumption, revealing a universe considerably stranger and considerably more restless in its expansion than anyone had previously suspected. For a brief flash, somewhere in the distant universe, more energy can be released in mere seconds than our sun will produce across its entire multi-billion-year lifetime. And from Earth, most of us would never even notice it happened. These sudden, extraordinarily energetic flashes are called gamma-ray bursts, and they rank among the most powerful individual events known to occur anywhere in the universe. They were first detected almost by accident in the late 1960s by satellites originally designed to monitor for secretive nuclear weapons testing on Earth, which instead picked up brief, intense bursts of gamma radiation arriving from deep space, entirely unrelated to anything happening on our own planet. It took years of careful observation and theoretical work afterward to properly understand what was producing them. The leading explanation for the longer variety of these bursts involves the collapse of an extremely massive, rapidly spinning star directly into a black hole. As the star's core collapses inward, the surrounding material forms a swirling, superheated disk around the newly formed black hole, and narrow, extraordinarily powerful jets of energy blast outward from its poles at nearly the speed of light. If one of these narrow jets happens to point directly toward Earth, even from a galaxy billions of light years away, our instruments can detect the burst clearly, despite the almost unimaginable distance involved. And yet, for all that raw, concentrated power, gamma-ray bursts remain effectively invisible without specialized instruments. They don't register as sound, obviously, and they don't produce anything the human eye could ever perceive directly. since gamma radiation sits far outside the narrow range of light our eyes are built to detect. A star's most violent possible death, capable of outshining an entire galaxy for a matter of seconds, can occur, be detected, be carefully studied, and quietly fade away again, without a single person on Earth ever noticing anything happened at all, apart from the handful of scientists watching data quietly scroll across a screen somewhere. An entire, previously unknown layer of the universe was discovered almost completely by accident, by an engineer who wasn't even looking for anything in space at all. He was simply trying to track down a source of annoying static. His name was Carl Jansky, and in the early 1930s, he was working for Bell Telephone Laboratories, tasked with identifying sources of radio interference that were disrupting transatlantic telephone communication. Using a large, rotating antenna he built specifically for the job, Jansky carefully tracked down several familiar sources of static, including distant thunderstorms. But one persistent, faint hiss of radio noise remained, one that didn't match any known source on Earth, and seemed instead to shift its position gradually across the sky over the course of each day, tracking not with the sun, but with the distant stars. Eventually, Jansky determined that this mysterious hiss was coming from the direction of the center of our own galaxy, the Milky Way. Without intending to, he had discovered that space wasn't only sending us visible light. It was also filled with a faint, steady murmur of radio waves, an entirely separate channel of information that had been arriving on Earth for the whole of human history, completely unnoticed, simply because nobody had yet built an instrument capable of detecting it. Jansky's discovery quietly launched an entirely new field, radio astronomy, which has since revealed enormous amounts about the universe that visible light alone could never have shown us, from the structure of distant galaxies to the ancient light we'll discuss in a moment. It's a fitting reminder that the universe's quiet isn't a single, simple silence. It's layered, with entire channels of information humming along invisibly, waiting patiently for someone curious enough and persistent enough to finally go looking for the source of a little unexplained static. There's a faint signal reaching Earth from every single direction in the sky, all at once, carrying a photograph of the universe from a time before a single star had ever ignited. We touched on this briefly during a previous night together, the cosmic microwave background, the ancient afterglow released once the early universe cooled enough to become transparent, allowing light to travel freely for the very first time. Tonight, it's worth returning to it through a slightly different lens, because this ancient light plays a central role in why the universe feels, and in many ways genuinely is, such a quiet place to observe from. This background signal isn't loud in any traditional sense, arriving instead as an extremely faint, extremely uniform whisper of microwave radiation, barely a few degrees above absolute zero, spread almost perfectly evenly across the entire sky. It was discovered accidentally in 1965 by two researchers, Arno Penzias and Robert Wilson, who were working with a highly sensitive radio antenna and kept encountering a persistent, faint background hiss they couldn't eliminate, no matter how carefully they cleaned their equipment or accounted for every plausible source of interference, even suspecting for a while that pigeon droppings on the antenna might be responsible. Eventually, they realized the hiss wasn't a flaw in their instrument at all. It was the universe itself, whispering the same faint note from every direction, the leftover glow from an event that occurred nearly 14 billion years earlier. What makes this discovery so central to tonight's subject is what it reveals about the deep, structural quietness of the universe. This ancient light has been traveling, largely undisturbed, for almost the entire history of the cosmos. passing through vast stretches of near-total emptiness without being scattered, absorbed, or drowned out along the way. It's a direct, working demonstration of the very stillness we've spent tonight exploring, a faint, ancient whisper that has managed to survive nearly the full span of cosmic history, arriving completely intact, simply because so much of the space it crossed had almost nothing in it capable of interrupting the journey. For decades, a small, patient community of scientists has been listening carefully to the vast quiet of the universe for a signal that might not be natural at all. And so far, in all that listening, they have heard nothing but ordinary cosmic static. This effort is known as SETI, the search for extraterrestrial intelligence, and it operates on a reasonably simple premise. If other civilizations exist elsewhere in the universe, and if any of them have developed radio technology comparable to our own, there's at least some chance that a deliberate or accidental signal, a genuine artificial pattern rather than the random noise produced by stars and gas clouds, might be detectable somewhere among the vast, quiet background of natural cosmic radio emissions. The scale of this listening effort is genuinely enormous. Radio telescopes involved in various search programs have scanned across wide swaths of the sky, across an enormous range of possible frequencies, sorting through staggering amounts of data in search of any pattern that couldn't be easily explained by known natural sources, like pulsars, distant galaxies, or the sun's own routine activity. A small handful of intriguing, unexplained signals have turned up over the decades, including a notably strong, brief burst detected in 1977 that researchers nicknamed the WOW signal, after an excited note scrawled in the margin of the printout by the astronomer who first noticed it. Despite considerable follow-up effort, no confirmed repeat of that particular signal, or any other similarly compelling candidate, has ever been found. In its own way, this decades-long silence carries its own kind of significance, whatever the eventual answer turns out to be. Either the universe genuinely is as quiet as it appears, empty of any other civilization currently capable of, or interested in, reaching outward the way we occasionally do, or such signals exist somewhere out there, patient and real, simply still waiting for the right instrument, the right moment, or the right stretch of listening to finally be noticed among everything else quietly filling the sky. Billions of years from now, if anything remains to look upward, the night sky will offer a far quieter view than the one you're imagining tonight, thinned out almost entirely by the same accelerating expansion we discussed a little earlier. As dark energy continues driving the universe's expansion faster and faster, distant galaxies will gradually be carried beyond the cosmological horizon, the boundary past which their light can no longer ever catch up to an observer on Earth, or wherever an observer happens to be by then. Over enormous stretches of time, this means fewer and fewer galaxies will remain visible from any single vantage point, not because they've been destroyed or have moved anywhere unusual, but simply because the space between here and there will have stretched too far, too quickly, for their light to ever complete the journey. A future observer looking upward, far enough ahead in cosmic history, might see only the merged, gravitationally bound remnant of our own galaxy and its closest neighbors, an island of stars drifting alone in an otherwise increasingly blank, increasingly silent sky. The grand structure discussed earlier tonight, the crowded filaments, the sprawling clusters, the countless overlapping galaxies filling deep telescope images today would have thinned considerably by then, most of it pulled permanently out of view, leaving behind a universe that looks, and in every meaningful sense actually is, far quieter than the one currently surrounding you. There's something worth sitting with in that. The universe we're living inside right now, tonight, busy with visible galaxies, filled with detectable light arriving from every direction, may be remembered, if anyone remains far enough in the future to look back on it, as one of the noisier, more crowded chapters in an otherwise very long and very gradual settling into quiet. If Earth's atmosphere were removed just far enough from the surface, a familiar, everyday scene, footsteps, a closing door, the hum of a passing car, would begin, one by one, to vanish into total silence. It's worth remembering, tucked into tonight's subject, that sound isn't something the universe generally offers by default. It's something Earth's own thick blanket of atmosphere happens to make possible, a genuine, if easily overlooked, exception to how most of the universe actually behaves. On Earth, that atmosphere is dense enough, all the way up to a significant altitude, to carry sound reliably across considerable distances. But climb high enough, into the thinning air near the edge of space, and that reliability quickly begins to break down, sound growing fainter and less predictable as fewer and fewer molecules remain available to pass a pressure wave along. Other worlds in our own solar system offer their own strange variations on this theme. Mars, with an atmosphere less than 1% as dense as Earth's, would carry sound only faintly and imperfectly, and recordings actually captured by instruments on the Martian surface confirm that sound there travels more slowly and fades more quickly than it would here, and even shifts in pitch depending on the specific mixture of gases involved. Venus, by contrast, has an atmosphere so thick and dense that sound there would likely carry unusually well, though the crushing pressure and searing heat would make actually experiencing it rather impractical for almost any visitor. And on some of the more distant moons, like Saturn's moon Titan, with its thick, hazy nitrogen atmosphere, sound would behave differently still, deeper and slower than the sound familiar to us here on Earth. It's a small, oddly comforting thought to carry into sleep. The ordinary, everyday sounds surrounding a comfortable evening, a settling house, distant traffic, the quiet rhythm of your own breathing, aren't universal at all. They're a genuine, fragile privilege, made possible by the specific thickness of the air currently, quietly, surrounding you, an exception carved out of a universe that, left to its own devices, would prefer almost total silence instead. In 1977, a golden record was launched into space carrying the sounds of Earth, greetings in dozens of languages, birdsong, thunder, laughter, a mother's kiss, deliberately sent outward into the one environment in the entire universe where none of it could ever actually be heard. This was the Voyager Golden Record, attached to both Voyager 1 and Voyager 2, the same spacecraft discussed on a previous night together, now drifting far beyond the edge of our solar system, carrying a carefully curated collection of Earth's sounds and images, intended as a kind of message in a bottle, cast out into the vast quiet in case some distant, unimaginable listener might one day find it and choose to play it. There's a quiet, almost tender irony tucked into that gesture, one worth sitting with tonight. The record itself can't actually produce any sound on its own while drifting through space. It requires a physical stylus, careful handling, and a listener deliberately choosing to play it, the same as any ordinary vinyl record here on Earth. Out there, surrounded by the same profound silence we've spent tonight exploring, it exists instead as pure potential, a small, patient container of sound, waiting in absolute stillness for a set of ears, or something like ears, that may never actually arrive. And yet, the gesture itself carries meaning regardless of whether it's ever heard. It represents something quietly hopeful about how humanity chose to greet a mostly silent universe, not with a demand to be noticed, but with an offering, gentle and unhurried, cast outward into a silence too vast to reasonably expect a reply, sent anyway, simply because the sending itself seemed worth doing. There exists a room, built here on Earth, so thoroughly engineered to absorb every trace of sound that people who step inside sometimes cannot bear to stay for more than a few minutes at a time. This is called an anechoic chamber, a specially designed space lined with thick, angled foam wedges that absorb nearly all sound reflections, along with heavy soundproofing that blocks almost every outside noise from entering at all. Certain chambers, including one built for testing audio equipment, have been measured at background sound levels so low they're recorded in negative decibels, a level of quiet more extreme than most people ever encounter in ordinary life, closer, in its own artificial way, to the profound silence of open space than almost anywhere else on Earth. What's genuinely strange is how people tend to react once inside. Rather than finding the experience peaceful, many visitors report the opposite, an unsettling, disorienting quiet that quickly becomes uncomfortable. Deprived of the usual, mostly unnoticed hum of everyday sound, air conditioning, distant traffic, the soft ambient noise most environments carry without anyone consciously registering it. Some visitors report becoming acutely aware instead of internal sounds normally lost in that background noise, their own heartbeat, their own breathing, even, according to some accounts, the faint sound of blood moving through their own ears. Total silence, it turns out, isn't experienced by most people as restful. It's experienced as strange, even mildly disorienting, a reminder that human beings seem to be built expecting a small, steady undercurrent of sound in the background of their lives, rather than nothing at all. It's worth holding that thought gently tonight, as you drift towards sleep surrounded by whatever small, ordinary sounds happen to be present in your own room right now. Unlike the true, total silence of deep space, or the engineered silence of a chamber built specifically to remove every trace of sound, the soft, familiar quiet of an ordinary room, however still it might feel, is almost never actually empty. There's usually still just enough sound present, quiet and unnoticed, to keep the mind comfortably, gently anchored, right up until sleep finally takes over completely. The very quietness that fills most of the universe isn't simply an empty backdrop for everything else to happen against. It might be one of the most important conditions allowing anything, anywhere, to ever be discovered or understood at all. Consider what would happen if space weren't so overwhelmingly empty. If the vast distances between stars and galaxies were instead filled with even a modest amount of gas or dust, light traveling across those distances would be scattered, absorbed, and distorted constantly, arriving badly degraded, if it arrived at all, especially after crossing distances of millions or billions of light years. The remarkably empty, remarkably quiet nature of interstellar and intergalactic space is precisely what allows light to travel such staggering distances while remaining largely intact, carrying accurate, detailed information about its source all the way to whatever distant telescope eventually happens to catch it. This is part of why astronomers have been able to reconstruct so much of the universe's history with such surprising precision, mapping the structure of galaxies billions of light years away, measuring the exact composition of distant stars, tracing the faint, ancient light of the cosmic microwave background back to the very edge of observable time. None of that would be possible in a noisier, busier, more cluttered universe. The silence isn't simply the absence of something more interesting happening elsewhere. It's the very condition that makes careful, distant observation possible at all, the quiet, undisturbed channel through which nearly everything we've ever learned about the universe has managed to reach us. There's something worth carrying into sleep in that idea. Quiet, so often treated as simply an absence, an empty gap where something louder might otherwise be, can also be the very thing that allows delicate, distant signals to survive their journey completely intact. The universe's vast stillness isn't a void separating meaningful things from one another. In its own patient way, it's part of what allows meaning to travel as far and as clearly as it does. Even the most violent, energetic events astronomers have ever confirmed produce absolutely no sensation of force or motion for anyone watching safely from a distance, because space offers nothing solid for that violence to push against. On Earth, an explosion produces far more than light and heat. It produces a genuine, physical shockwave, a wall of rapidly compressed, rapidly moving air capable of shattering windows, flattening structures, and knocking a person clean off their feet from a considerable distance away. That shockwave is, at its heart, exactly the same kind of pressure wave responsible for ordinary sound, just far more intense, and it depends entirely on the same thing sound always depends on: a medium of matter, densely packed enough to transmit that violent compression outward from its source. A supernova, one of the most energetic events the universe is capable of producing, does actually generate an initial burst of material moving outward at extraordinary speed, a genuine physical shockwave within the immediate surroundings of the exploding star itself, where enough matter still exists nearby to carry it. But that shockwave weakens rapidly as it expands outward, and once it reaches the emptier reaches of interstellar space, with far too little matter remaining to sustain it, that once violent wave of compressed material thins out into something closer to a gentle, gradually fading breeze, rather than continuing on as the devastating force it briefly was near its source. This is part of why distant cosmic violence, however extreme, poses no physical danger to safely distant observers in the way an equivalent explosion would on Earth. There's no invisible force reaching across the emptiness to knock anything over, no pressure wave capable of surviving the enormous, largely empty distances separating most objects in space from one another. The universe's violence, it turns out, stays remarkably close to home, fading quickly into the same deep, forgiving quiet that fills nearly everything surrounding it. A spacecraft, once released into open space with its engines off, will keep drifting onward at exactly the same speed, in exactly the same direction, for as long as nothing else interferes. And the very quiet emptiness we've spent tonight exploring is the reason why. On Earth, moving objects are constantly slowed by friction and air resistance, invisible forces created by countless collisions with surrounding air molecules, gradually converting motion into heat until, left alone, nearly everything eventually comes to rest. A ball rolled across a field slows and stops. A bicycle coasting downhill eventually settles to a halt on flat ground. This constant, gentle drag is so thoroughly woven into everyday experience that it's easy to assume it's simply how motion naturally behaves. Space tells a different story, precisely because it offers so little matter for a moving object to collide with. Without a meaningful atmosphere to push against, a spacecraft experiences no appreciable air resistance at all, and without any other outside force acting on it, it continues along its original path indefinitely, coasting quietly onward, requiring no further fuel or effort to maintain that motion. The Voyager probes discussed on a previous night together have been drifting outward for decades now, with their main engines long since powered down, and they will likely continue drifting for millions of years to come, gradually slowing only slightly under the extremely faint, distant pull of gravity from stars they'll never actually approach closely. This isn't some special exception granted only to spacecraft. It's simply Newton's first law, in its purest and most visible form, playing out constantly, quietly, across the whole of space. Motion, once begun, wants nothing more than to continue exactly as it is, forever, and the universe's profound emptiness is precisely what allows that quiet, patient continuation to actually happen, largely undisturbed, for as long as nothing gets in the way. Deep beneath the surface of certain collapsed stars, tiny shifts and cracks occur that release more energy in an instant than the sun produces across many years, and from Earth, we detect none of it as sound, but as a sudden, precise change in the timing of a distant cosmic beacon. These collapsed stars are called neutron stars, discussed briefly on a previous night together, and some of them, known as pulsars, spin remarkably fast while sweeping narrow beams of radiation across space, detectable as extremely regular, rhythmic pulses whenever one of those beams happens to sweep across Earth, not unlike the regular flash of a lighthouse. Because pulsars spin with such extraordinary, reliable regularity, astronomers can measure their timing with exceptional precision, often accurate to within millionths of a second over long stretches of observation. Occasionally, though, astronomers notice a sudden, tiny disruption in that otherwise near-perfect rhythm, a small, abrupt jump in the pulsar's spin rate, called a glitch. The leading explanation involves the neutron star's rigid outer crust suddenly settling or cracking slightly, adjusting to internal stresses built up as the star's interior continues to slowly change, not unlike the way Earth's own crust occasionally shifts during an earthquake, releasing built-up tension all at once. On a neutron star, incredibly dense and under incomprehensible internal pressure, even a shift measured in mere millimeters can release energy on a scale difficult to properly imagine, and yet register on Earth only as a tiny, precise deviation in the arrival timing of its otherwise perfectly steady radio pulses. It's a strange, quiet way to detect genuine cosmic violence, not through sound, not through light bright enough to notice directly, but through the smallest possible disruption in an otherwise perfect, distant rhythm, a whisper of disturbance carried not by any wave of sound, but by the careful, patient timing of astronomers watching a beacon blink steadily from many thousands of light years away. Long after the last star has faded and the last black hole has slowly evaporated away, astronomers expect the universe to settle into something that isn't merely quiet, but close to a kind of true, final stillness, one where even the concept of an event may eventually stop meaning very much at all. Physicists sometimes call this far distant future the heat death of the universe, a name that sounds more dramatic than the reality it describes, since it involves no sudden ending, no explosion, no dramatic final event of any kind. Instead, it describes a slow, extraordinarily patient process, playing out across a length of time that makes even the vast timescales discussed earlier tonight look almost immediate by comparison. As stars burn out and new star formation gradually ceases, as black holes slowly radiate away their mass through the Hawking radiation discussed on a previous night together, and as the universe's ongoing expansion continues stretching everything further and further apart, energy and matter are expected to spread out ever more thinly and evenly, until eventually, almost nothing remains capable of doing anything at all. No more temperature differences to drive activity, no more concentrated energy to power a single further event. In this far future scenario, the universe wouldn't simply be quiet the way tonight's earlier facts have described. It would be still in an even deeper, more thorough sense, a state where meaningful change essentially stops occurring altogether, where the very distinction between one moment and the next begins to lose its usual meaning, since nothing remains to mark any difference between them. It's worth being honest that this lies almost unimaginably far in the future, trillions upon trillions of years away, so distant that it holds no real bearing whatsoever on tonight, this year, or any stretch of time a person could reasonably hold in mind. But there's something quietly quieting, appropriately enough, in knowing that the vast, patient silence surrounding tonight's exploration isn't simply where the universe happens to be right now. It may be the direction the entire universe has been gently, unhurriedly settling toward, the whole time, long before you were here to notice it, and long after you'll be here to wonder about it further. Every single second, our sun releases a steady stream of charged particles rushing outward through the solar system at speeds often exceeding 1,000,000 miles per hour, and despite that constant, ferocious motion, it makes no sound whatsoever. This is the solar wind, discussed briefly on a previous night in connection with Voyager's long journey outward, and it's worth returning to here for what it reveals about the difference between motion and sound. On Earth, wind is loud precisely because it's air, dense, plentiful air, pushed rapidly past solid objects, creating turbulence and pressure changes that our ears register instantly as a familiar rushing or howling noise. The solar wind carries a name that invites the same expectation, but it behaves nothing like its earthly namesake. It consists of particles spread so thinly across such enormous distances that, despite its incredible speed, there simply isn't enough material present to create the kind of dense, colliding turbulence needed to produce anything resembling sound. When the solar wind does encounter something substantial, like a planet's magnetic field or atmosphere, the interaction can become dramatic and even visible, producing the shimmering auroras that appear near Earth's polar regions when charged particles collide with atmospheric gases high above the ground. But even that dramatic, glowing display remains, for the vast majority of observers, silent, a purely visual phenomenon rather than an audible one, despite centuries of scattered reports describing faint crackling or hissing sounds heard during particularly strong auroral displays. Scientists studying these rare claims have found some evidence that certain temperature inversions in the atmosphere, closer to the ground, may occasionally produce a genuine, very faint crackling sound during intense auroral activity, though this remains a subtle, uncommon, and still not fully understood effect, entirely separate from the aurora's actual source high above. For the overwhelming majority of its million-mile-per-hour journey outward, though, the solar wind moves in complete silence, rushing past planets, moons, and spacecraft alike, without ever producing so much as a whisper. One more example of just how much of the universe's motion unfolds entirely without sound, regardless of how fast or how forceful that motion actually is. The event that began the entire universe almost certainly did not produce a bang of any kind, and the very name most people use for it may be one of the most persistent, most understandable misunderstandings in all of popular science. The term Big Bang was actually coined somewhat dismissively by an astronomer who favored a different, competing theory, and the name stuck, catching on far more successfully than the idea it was originally meant to gently mock. And the name does carry an unfortunate implication, suggesting a sudden explosion, expanding outward into some larger, pre-existing empty space, complete with the kind of shockwave and roar we associate with explosions here on Earth. As we've discussed at length tonight, Sound requires a medium to travel through, and in the earliest moments of the universe's existence, there was no pre-existing space for an explosion to expand into in the first place, and certainly no outside medium capable of carrying any kind of sound away from the event. Space itself was the thing coming into being, not a container that something else exploded within. And yet, in a strange, genuinely wonderful twist, there really was something remarkably like sound present in the universe's earliest history, just not in the way the name Big Bang casually implies. In the few 100,000 years before the universe cooled enough to release the ancient light discussed earlier tonight, ordinary matter and light existed together as an extremely hot, dense plasma, and tiny variations in that plasma's density genuinely did behave like sound waves, real pressure oscillations, rippling outward from countless tiny regions of slightly higher density scattered throughout the early universe. Astronomers call these ripples baryon acoustic oscillations, and remarkably, their faint imprint is still detectable today, frozen into the large-scale distribution of galaxies across the observable universe, like the fossilized ripples of a pond long after the water itself has gone still. So the universe's true beginning wasn't a bang, loud or otherwise. But its earliest chapters really did include something genuinely close to sound, a brief, ancient acoustic hum, rippling through hot plasma for a few 100,000 years before falling permanently silent and leaving behind, quietly etched into the positions of galaxies scattered across the sky, the faint, patient echo of the very last sound the universe would ever produce on that kind of scale. Nearly every dramatic whoosh, rumble, and roar heard in a film or television scene set in outer space is, without exception, entirely invented, added deliberately by a sound designer working in a studio here on Earth, long after the actual footage was filmed. This is such a common and thoroughly ingrained cinematic convention that it rarely draws much notice, but it's worth pausing on tonight, given everything we've covered. Spaceships roaring past the camera, explosions thundering in the vacuum of space, distant planets humming with an audible atmosphere. None of it reflects how any of those events would actually sound, because, as we've spent the whole night establishing, they wouldn't produce any sound at all in the environment where they're depicted taking place. Filmmakers add these sounds deliberately, understanding perfectly well that they're inventing them, because pure, accurate silence, however true to the science, tends to feel oddly flat and undramatic to an audience conditioned by a lifetime of movies to expect motion and impact to come paired with corresponding noise. Even real recordings that seem to capture the sound of something happening in space are, without exception, actually translations of some other kind of data into an audible format, exactly like the gravitational wave chirp and the black hole's impossibly deep note discussed earlier tonight. Spacecraft have recorded genuine electromagnetic emissions from planets like Jupiter and Saturn, eerie, whistling, crackling patterns produced by charged particles interacting with each planet's powerful magnetic field. When scientists convert those electromagnetic recordings into audible sound, the results can be strikingly eerie and evocative, easily mistaken for some genuine ambient noise recorded out among the planets themselves. But like the gravitational wave chirp discussed earlier, these are translations, not recordings in the traditional sense, electromagnetic data given an audible voice by scientists choosing, deliberately and usefully, to let human ears make sense of information they couldn't otherwise perceive directly at all. It's a fitting note to end tonight's exploration on. Nearly everything that sounds like the universe, in film, in documentaries, even in genuine scientific recordings, has passed through some deliberate act of translation or invention along the way. The universe itself, left entirely to its own devices, remains exactly what we've spent the whole night quietly discovering. Something almost perfectly, patiently silent. A blazing fireball can streak silently across the night sky for several long seconds, and then, sometimes, without any obvious explanation, observers standing far below report hearing a faint crackling or hissing sound at the very same instant the fireball appears overhead, despite the fact that sound simply shouldn't be able to arrive that quickly. These bright, dramatic meteors are produced when a fragment of rock or ice, sometimes no larger than a pebble, enters Earth's atmosphere at extraordinary speed and burns up from the friction, producing a brilliant, fleeting streak of light. If the meteor is large or fast enough, it can also produce a genuine sonic boom, an actual pressure wave created as it displaces air faster than sound itself can travel. But that boom takes real time to reach the ground, typically arriving many seconds, sometimes even minutes, after the visible flash, exactly as you'd expect from sound traveling the ordinary way, limited by the ordinary speed of sound through air. What puzzled observers and scientists alike for a long time were separate, credible reports describing a different kind of sound, a faint hissing, crackling, or rustling noise heard by witnesses at the very same moment a bright fireball streaked overhead, with no delay whatsoever, which shouldn't be physically possible if the sound were traveling through the air in the ordinary way. These are now referred to as electrophonic sounds, and while the exact mechanism remains an area of ongoing research, the leading explanation suggests that the fireball's trail can generate very low-frequency radio waves, which travel at the speed of light rather than the speed of sound. If these radio waves reach a suitable nearby object, like dry hair, eyeglasses, or even certain vegetation, they can, under the right conditions, cause it to vibrate slightly, producing an actual, physically real sound heard by a nearby observer, without any traditional sound wave needing to travel from the sky at all. It's a strange, quietly delightful little mystery to end this particular thread on. A sound that seems to arrive instantly from something happening high overhead, not because sound has somehow broken its own rules, but because, once again, something has been faithfully translated, this time from light and radio waves into a very ordinary, very real vibration, close enough to the listener to finally, briefly, be heard. As Voyager 1 crossed the boundary of our solar system, discussed on a previous night together, its instruments captured something that scientists were able to convert into one of the closest things humanity has ever recorded to an actual sound of interstellar space itself. The spacecraft doesn't carry a microphone in the traditional sense, since there's nothing for an ordinary microphone to usefully detect in the emptiness it travels through. Instead, it carries an instrument capable of detecting oscillations in the surrounding plasma, the thin, charged particles that fill even the sparse reaches of interstellar space. As Voyager 1 passed beyond the heliopause, the boundary separating the sun's influence from true interstellar space, its instruments picked up plasma wave oscillations at a slightly higher, denser pitch than anything recorded while still within the solar wind's influence, a subtle but genuine shift confirming, alongside other measurements, that the spacecraft had truly crossed over into a new kind of environment. When scientists converted those detected oscillations into an audible frequency range, the resulting recording carries an eerie, almost otherworldly quality, a faint, shifting hum, rising and falling gently, utterly unlike anything typically associated with silence or emptiness. It isn't sound in the traditional sense we've spent tonight discussing, since it never traveled as an actual pressure wave through matter the way a voice or a footstep does. It's a translation, once again, of real, physical plasma activity into a frequency range human ears are equipped to notice and interpret. Still, there's something worth holding on to in that recording, however technical its true origin. It represents actual data, gathered by an actual instrument, further from Earth than almost anything else humanity has ever built, patiently translated into something we're able to sit with, quietly, for a moment, before letting it fade back into the vast, wordless quiet it came from. Astronauts who have spent extended time aboard the International Space Station consistently describe one particular sensation as among the strangest parts of returning to Earth: the sheer, overwhelming volume of an ordinary, everyday environment they had simply stopped expecting to notice. Life aboard the station is far from silent, filled with the steady hum of ventilation systems, cooling equipment, and other machinery essential for keeping its occupants alive. But that hum is remarkably consistent, unchanging, and entirely mechanical, without the constantly shifting, unpredictable texture of ordinary life on Earth. Birds, traffic, wind moving through trees, other people's footsteps, and voices layered together into the constantly changing background most of us grow up never fully noticing at all. Several astronauts have described the return to Earth's ordinary, layered soundscape as genuinely disorienting at first, almost overwhelming in its variety and unpredictability, after months spent surrounded by the same steady, familiar mechanical hum, day after day, without pause. Some astronauts have also spoken about the profound, almost meditative quiet available during moments spent looking out a window at the Earth or the stars beyond, a stillness made all the more striking by the knowledge of just how much genuine emptiness and silence surrounds their small, humming, life-sustaining vessel. Chris Hadfield, a Canadian astronaut who commanded the International Space Station and later became known for candidly describing daily life aboard it, has spoken about how quickly the human mind adjusts to an entirely new definition of normal, treating the station's mechanical hum and the vast silence surrounding it just beyond a thin metal wall as simply the new, unremarkable backdrop of everyday life. There's something worth sitting with in that adjustment tonight. The line between overwhelming noise and profound silence, it turns out, isn't fixed by the universe alone. It shifts quietly and naturally, according to whatever a person has grown accustomed to calling ordinary, whether that happens to be the layered, unpredictable soundscape of an evening on Earth, or the steady mechanical hum of a small, bright vessel drifting quietly through the vast, wordless dark surrounding it. Saturn's rings, a wide, glittering band of ice and rock stretching across hundreds of thousands of miles, have been quietly, continuously humming with their own faint electromagnetic activity the entire time, long before any instrument arrived close enough to notice. The Cassini spacecraft, which spent 13 years orbiting Saturn before deliberately plunging into the planet's atmosphere at the end of its mission, carried an instrument specifically designed to detect radio and plasma wave emissions, similar in spirit to the instrument aboard Voyager discussed a moment ago. As Cassini passed close to Saturn's rings, it detected a distinctive pattern of electromagnetic activity, created as tiny charged ice particles from the rings interacted with Saturn's powerful magnetic field, effectively raining down along magnetic field lines connecting the rings to the planet's upper atmosphere. When scientists converted these detected emissions into an audible frequency range, the resulting recording carries a strange, almost musical quality, rising and falling in pitch, closer in character to static or wind than to anything resembling an actual voice or instrument, and yet distinct enough that mission scientists gave it its own name, describing it as the sound of Saturn's rings raining onto the planet. As with every other recording discussed tonight, it's worth being clear about what it actually represents. No sound wave ever traveled the roughly 1 billion miles separating Saturn from Earth. What traveled that distance was data, carefully measured electromagnetic activity, translated afterward into something a human ear could meaningfully process and appreciate. It's a fitting image to hold on to, tucked among so many other examples tonight of real, physical events, translated patiently from silence into something we're able to notice at all. An entire ring system, vast and ancient, quietly interacting with its planet's magnetic field for untold ages, completely unheard, until a small, patient spacecraft finally arrived close enough to listen, and someone back on Earth thought to ask what that listening might sound like. When a tiny fragment of space debris, sometimes no larger than a grain of sand, strikes the International Space Station at several miles per second, the impact registers clearly on the station's instruments, and yet nobody aboard hears a single sound. Even in low Earth orbit, hundreds of miles above the ground, the environment remains close enough to a true vacuum that ordinary sound simply cannot travel through the empty space surrounding the station's outer hull. When a small piece of debris strikes the exterior, the impact itself produces a genuine, physical vibration, a shockwave passing directly through the station's solid metal structure. Exactly the same basic principle behind sound traveling through any solid material, wood, stone, or metal, all of which can carry vibrations quite effectively, even when the empty space surrounding that material cannot. This means the impact can, under the right circumstances, actually be heard, or at least felt, faintly, by astronauts aboard the station, not because the sound traveled to them through the vacuum outside, but because it traveled through the solid structure of the station itself, the same way you might feel, and even faintly hear, a knock on a wall from an adjoining room, carried entirely through solid material rather than through open air. More often, though, such impacts are simply too small or too far from any occupied module to be noticed directly at all, registering instead only on sensitive instruments specifically designed to monitor the station's structural integrity for exactly this kind of hazard. It's a small, fitting reminder of just how conditional sound really is, dependent entirely on finding the right material to travel through. The same tiny impact that would produce an unmistakable crack if it struck something out in the open air of Earth becomes, in the vacuum of orbit, something closer to a private, structure-born murmur, felt only by whatever solid material happens to be directly connected to the point of impact, and utterly silent to anything, or anyone, not touching that same unbroken structure. One of the most volcanically active places in the entire solar system produces no sound whatsoever, despite hosting eruptions violent enough to launch material hundreds of miles above its own surface. This is Io, one of Jupiter's 4 largest moons, squeezed and stretched continuously by the powerful, competing gravitational pulls of Jupiter and its neighboring moons, a process called tidal heating. That constant flexing generates enormous internal heat, enough to keep Io's interior partially molten and drive hundreds of active volcanoes across its surface, making it, by a considerable margin, the most volcanically active body anywhere in the solar system, including Earth. Some of Io's eruptions launch plumes of sulfur and other material to heights that would dwarf the tallest volcanic eruptions ever recorded on Earth, rising so high that they briefly escape the moon's own thin atmosphere entirely. And yet, exactly as we've spent the whole night establishing, none of that violence produces the faintest sound beyond Io's own immediate surroundings. Io's atmosphere is exceptionally thin, far too sparse to carry sound effectively even close to the site of an eruption, and the surrounding space separating Io from any potential observer offers nothing at all to carry sound any further. A moon capable of hosting eruptions more dramatic than anything Earth has ever produced remains, from any meaningful distance, every bit as silent as the emptiest stretch of interstellar space discussed earlier tonight. Spacecraft that have photographed Io's eruptions in detail, capturing plumes rising dramatically against the blackness of space, have never once recorded any accompanying sound, and never could, no matter how close they managed to approach. It's a striking reminder of just how completely sound depends on circumstance rather than intensity. The violence is real, dramatic, and extensively documented. The silence surrounding it, at any distance beyond Io's own thin, struggling atmosphere, is every bit as real and complete. There's a kind of silence in the universe that has nothing to do with the absence of sound at all, and everything to do with a substance that appears to make up more of the universe's total mass than everything visible combined. We discussed dark matter on a previous night together, the mysterious, invisible material inferred from its gravitational effects on galaxies, detectable through its pull, yet undetectable through light, sound, or any other conventional means. It's worth returning to briefly here, through the specific lens of tonight's subject, because dark matter represents perhaps the most thorough kind of silence physics has ever proposed, quieter even than empty space itself. Ordinary matter, even when spread thin enough to prevent sound from traveling through it, still interacts constantly through electromagnetic forces, colliding, radiating light, absorbing and reflecting energy in countless small ways. Dark matter, as far as current evidence suggests, does essentially none of this. It appears to interact with ordinary matter and with light almost exclusively through gravity, passing through planets, through stars, through your own body right now, without colliding, without radiating, without producing so much as a flicker of interaction beyond its steady, patient gravitational pull. If ordinary matter's silence, discussed throughout tonight, comes from simply being spread too thin to carry sound, dark matter's silence runs deeper still, a substance that may not be capable of producing anything resembling a collision at all, regardless of how densely it happened to be packed together. It's a strange, quietly humbling thought to end this particular thread on. The universe's silence, so thoroughly explored tonight through vacuum and distance and the physics of sound waves, may not even be the deepest silence available. Somewhere, threaded invisibly through every galaxy, including our own, there may be an entire form of matter outweighing everything visible, moving through the universe in a silence more complete than empty space itself has ever managed to offer. Even in the rare, denser pockets of space capable of carrying a genuine sound wave, there is one thing that could never happen out there, no matter how loud the original sound, or how perfectly reflective the surface it happened to strike: an echo. An echo, on Earth, depends on two things working together: a medium capable of carrying sound, and a solid, reasonably distant surface capable of reflecting that sound back toward its source, arriving late enough afterward for a listener to distinguish it clearly as a separate, repeated sound rather than simply part of the original. Even in the sparse gas clouds surrounding a galaxy cluster, dense enough, as we discussed earlier tonight, to carry an actual, genuine sound wave, an echo would still be extraordinarily difficult to produce, since space so rarely offers the kind of clean, solid, well-positioned reflecting surface needed to bounce a sound wave back cleanly toward its point of origin, rather than simply letting it continue spreading outward, thinning gradually until it fades away entirely. This absence carries a certain quiet poetry to it, fitting neatly alongside everything else discussed tonight. An echo is, in its own small way, a kind of memory, a sound repeating itself, briefly, after its original moment has already passed. The universe, for the most part, doesn't offer that kind of repetition. Sound, on the rare occasions it manages to exist out there at all, simply moves outward, once, and continues on, fading gradually into the surrounding emptiness, never circling back to remind anything of where it came from. There's something worth sitting within that, gently, on a night devoted to quiet. Perhaps rest, at its best, works a little like the universe's own version of sound. Not something that needs to echo, circle back, or repeat itself to prove it mattered. Simply something allowed to happen once, fully, and then permitted to fade, undisturbed, into whatever stillness comes next. For a scientist who cannot see, the usual tools of astronomy, telescope images, graphs, and charts glowing on a screen, offer very little on their own. And yet some of the most meaningful discoveries in recent astronomy have come from turning starlight into something that can be heard instead. This is the work of sonification, converting astronomical data, brightness, wavelength, timing, into sound, a technique touched on several times throughout tonight in connection with gravitational waves, black hole notes, and recordings from distant spacecraft. For most researchers, sonification offers a helpful, sometimes striking alternative way of exploring data. For blind and visually impaired astronomers, it can offer something considerably more essential: direct, meaningful access to the universe's data at all. The astrophysicist Wanda Diaz-Merced, who lost her sight while working toward a career in astronomy, became one of the leading advocates for exactly this approach, developing techniques to convert telescope data directly into sound, allowing her to detect patterns, fluctuations, and subtle features in stellar and gamma-ray data that might otherwise have gone unnoticed even by sighted researchers relying on visual graphs alone. In some cases, her sonified data revealed genuine features that had been technically present in the visual charts the entire time, simply easier to notice by ear than by eye. A reminder that different senses aren't simply substitutes for one another, but can genuinely reveal different aspects of the very same information. It's a quietly moving thought to carry into the closing stretch of tonight's exploration. Across the whole of tonight's journey, we've discussed a universe that offers almost nothing to the ear directly, an overwhelming, near-total silence stretched across nearly everything. And yet, through patient, careful translation, that silence has been persuaded, again and again, to speak, not only to instruments and to careful measurement, but to actual listening, human ears, sometimes quite literally opening an entire universe to someone who could access it in no other way. Let's return, gently, to the three questions from the very start of the night. If the loudest event imaginable happened right next to you in space, would you hear anything at all? No, not a whisper. The loudest possible event and total silence can, and do, happen in exactly the same place, at exactly the same moment, without any contradiction at all. Is silence really the same thing as emptiness? Or is it doing something quietly, all on its own? It's doing something. It's the very stillness that lets ancient light cross billions of years intact, that lets a spacecraft coast for decades without a drop of fuel, that let one faint, patient signal survive 14 billion years just to reach the antenna that finally caught it. And if the universe is growing quieter with every passing year, what does that mean for a night like this one? Perhaps only that tonight is, in its own small way, a little more alive than most of what's still to come. Whatever quiet you find in this room right now sits inside a universe that's still humming, still drifting, still busy in its own unhurried fashion, and that's a rather lovely thing to be a small, quiet part of. You don't need to carry any of this with you into sleep. The stillness we've spent tonight exploring doesn't ask to be remembered. It simply continues, the way it always has, whether or not anyone happens to be listening. So let yourself settle now, the way starlight settles across an empty field, the way a held breath finally, gently lets go. There's nothing left to listen for tonight. No signal to wait on, no distant chirp to catch, no message that needs answering before morning. Just this room, this quiet, this breath, and the vast, patient stillness holding all of it, gently, exactly the way it holds everything else. Thank you for spending these hours here, in Somniora Mind, one quiet mind at a time. Rest now. You've earned it. Good night.